Okay, so let's make a very short review. We are talking about liquid level systems in which we have tanks with different heights, and there are flows to tanks and to in and out. Our main equation is the conservation of mass, which says that accumulation is equal to mass in minus mass out, which can be written in mathematically. Time rate of change of mass in the tank is equal to the rate of mass in minus the rate of mass out. Now, if you take a tank with with no holes to it, that is, you are just filling the tank, you can show that the equation that describes the tank is ADH dt is equal to Q, like this one, okay, by this derivation over here. And we show that this is analogous to electrical capacitance. In electrical capacitance, the current is equal to C times dV dt. Here, the flow, which is the flow variable, as you know, this is again the flow variable, Q, is equal to capacitance, which is the area of the tank, times change in height, which is analogous to change in voltage. Actually, this change in height is, as we will be seeing, is related to the change in pressure. And pressure is analogous to the voltage in fluid systems. So that's what we have. Let's make our tank a little bit more complicated. Let's say that you have a flow into the tank, as again before, but now there is also flow out. So this is the height. There is the area and so on. This is Q in, and this is Q out. Q in and Q out are volumetric flow rates in meters cubed per second, as we see. Okay, now we have the equation that describes this system is ADH dt is equal to Q in, as before, there is nothing different here, minus there is the output flow, Q out. Okay? We didn't describe this Q out yet. Q out is actually should be dependent on the system variables. And in order to do that, we have to define something which I will call the fluid resistance. We have defined the fluid capacitance, as you remember, now, which is the area of the tank. Now let's talk about the fluid resistance. Let's say that you have a pipe, like this one. You have, most of you have taken fluid mechanics, I guess. Let's say that this pressure is P1 here at one end. P2 is the pressure at the other end, and there is flow, Q, okay? Well, you can show that this flow is, the pressure drop is actually somehow, especially if you have laminar flow, the pressure drop, delta P, which is P1 minus P2, okay, is proportional to the flow rate, okay? The more the flow rate, the more pressure drop, I guess, Q. But then there is the some kind of a resistance to the flow. For example, for laminar flow, you can show that RF is I don't want to, it is 128 mu L divided by pi d to the 4, etc. It doesn't matter. This is called the fluid resistance. So we can write the change in pressure in a fluid system is flow divided by the fluid resistance. Okay, this fluid resistance is dependent on system parameters. The more the length of the pipe is, the more fluid resistance, etc. This is quite similar to, as you remember, I over R. Sorry. I think I made a mistake here. Yeah, this shouldn't be, I shouldn't be dividing it, I should be multiplying it. Okay. Q times RF, and this is also Q times RF. QRF, okay. The pressure drop is proportional to the resistance, of course. Delta V is equal to IR is the electrical term, okay? The resistance is proportional to viscosity, length, and inversely proportional to the diameter, etc., of the tank. So this is the resistance in laminar flow, but in turbulent flow, in which the Reynolds number is high, you can show that the pressure drop is the turbulent resistance times flow, not flow, but flow squared. But it doesn't matter. We usually take the linear relationship. This is a nonlinear relationship, as you see. But we will be taking this relationship in our equations. Change in pressure, delta P, is proportional to RF times Q, okay? This is the linear relationship for a tank. And we show this usually we show this by something like this. The fluid resistance is shown by something like two triangles, which is a bit like a valve, okay? And we say P1 on this side, P2 on that side. There is flow, Q, and this is RF. And again, the relationship Q is equal to delta P over RF. Okay, fluid resistance. It is not just the pipes, it is also in the orifices, for example, you have fluid resistance, or if you have bends in the pipe, that causes pressure drop and so on. So we always have some kind of pressure drop inside for the flows, as you know from fluid mechanics. Now let's take our tank example. Let's say that you have flow coming in. You have a tank. And this tank is connected to the outer world by a pipe, which has a fluid resistance, as we have said, like this. This tank has a height, h. This is Q in, this is Q out, okay? This is RF, if you like. The tank has an area of A, which is the capacitance, okay? Now, what is the pressure here? The pressure is the atmospheric pressure outside when the tank comes in. So it is atmospheric pressure here. It is atmospheric pressure here. What is the pressure here at the bottom of the tank? Let's call it P1. What is this P1 equal to? We assume hydrostatic pressure distribution, let's say. Because of the height of the water in the tank, it is rho times G times H, right? Plus the atmospheric pressure, actually. Isn't it? P1. So we have written as before area times dH dt was equal to Q in, flow in minus flow out, which is Q out. But flow out is, as we have written above, is change in pressure, which is P1 minus P atmospheric, let's say, divided by RF, right? But P1 is rho GH plus P atmospheric minus P atmospheric divided by RF. So Q out is simply rho GH over RF, isn't it? So I can write this equation as follows: AdH dt equals Q in. Now I have Q out. Q out is rho GH over RF, whatever that RF is. So this minus sign can be carried to this side. Okay. And I'll do something. This carrying this around this RF all the time is a little bit cumbersome. So I will define for the heights 1 over R is going to be rho G over RF. Okay. So R is equal to, if you like, what will it be? RF over rho G, right? So I'll carry this to the other side and write the following equation: AdH dt plus H over R is equal to Q in. Which is our equation for filling of a tank that has an input and an output. This is as you see, a first order differential equation. It has a dH dt term, it has a H term, and it has a Q in term. Okay. The model is a linear one. Well, I could have kept this rho G term, but this rho G term will be carried around all the time. If you use pressures as your variables, you can use maybe rho G term, but if you use, the heights, you can just define a new R term for your height and use that RF divided by rho G as your new resistance. That will be easier to carry around. Now, remember that if you have a tank, let's say that if you start filling a tank which has an output, let's say this is T, this is H of T. Physically, let's think about what will happen when you start filling a tank. in the beginning, you have zero height, okay? Yeah, there is no water in the tank. So you open the tap here in the at the top, and flow starts coming in. If the flow starts coming in, and if there is no flow output, actually, you are going to have the following. If this let's say outlet is closed, you will have the height would be increasing and increasing and increasing, but until it gets filled, of course. You know, you get it up to a point where you have tank is full here. Then it floods. Okay, this is H max, if you like. This is what happens when there is no outlet. Okay, so here in this case Q out is 0. If this is the what happens if the Q out is not 0? If the Q out is not 0, there will be flow going out proportional to the height. As the height increases, the flow in the tank is going to increase, and eventually you will get to a curve like this, something like this, okay? In which Q out at the steady state will be equal to the input flow, and the height will not be increasing anymore, okay? Q out and Q in will be equal to each other, and the height change in height will be 0 there. So this will be a steady state for the tank, actually. When this thing, you know, levels out with 0 derivative, this is called the steady state, okay? So this is the behavior of the tank with an output flow when there is a flow coming in. This is first order system response. And as a matter of fact, for example, this system is exactly the same as the electrical system, which is like this, okay? If this is VI, if this is VO, this is C, this is R, okay? And the equations that describe this system is more or less the same, actually. For example, in the electrical system, you have RC This is the electrical equation. In this equation, as you see, we wrote it in terms of Q in, but we can write it in terms of height, in terms of Q out, in terms of height. For example, we can say that Q out is equal to H over R, right? Yes, H over R is the Q out term. So Q out dot would be H dot over R. So H dot is going to be R times Q out dot, and H will be equal to R times Q out. Okay. So when I write out this equation, the equation in this box, in terms of Q out, I will get the following equation. A times dH dt. dH dt is RQ out dot. R dQ out dt plus H over R. H over R. H is R times Q out divided by R is just Q out is equal to Q in. Okay. Look at these. This is the equation for the tank. This is the equation for the resistance and capacitance system. And this is the equation for the tank. As you see, they are, well, very, very similar to each other, okay, in terms of variable. So this is the electrical equation. This is the tank equation, fluid equation. Okay, well, you don't have to have just one tank. You might have multiple tanks. You can have, for example, 2 tanks in which the following is the case. Let's say you have flow coming into one tank. And 2 tanks are connected to each other by a fluid resistance. And then in the second tank, there is a flow going out. This is Q in. Q in comes to the first tank. It might have come to the second tank as well. This is H1. This is H2. It has an area of A1. This has an area of A2. This is R1. This is R2. And this is Q. So we write the equation, the continuity equation, or the conservation of mass equation, which is the same thing, for both tanks. And for example, for tank 1, you will get 2 equations in this case, because you are writing equations for each tank. A1 times dH1 dt will be equal to input flow minus the output flow. Output flow is what? This is Q out, let's say 1. Q out 1. What is Q out 1? It is the pressure between these 2 points. But the pressures between these 2 points is proportional to H1. This is proportional to H1, this point. This point's pressure is proportional to H2. So it is H1 minus H2 over R, okay? R1. So the H1 equation has an H2 term in it. So the equations are kind of coupled, as you see. In the second equation, well, for the tank 2, you have the rate of change of the volume inside the tank, which is this term, AdH dt, is equal to, it is Q out 1. What is Q out 1? It was, this one is not a negative term, it is a positive term now. H1 minus H2 over R1 minus the flow out, which is H2 over R2. Is this clear?
Yes, hocam.
Well,
Hocam,
yes.
could you please explain the H1 minus H2 terms again?
Okay. you see, let's say that there is pressure P1 here, there is pressure P2 there, okay? What is P1 equal to? Rho G H1, right? What's P2 equal to? It is rho G H2. So the Q out should be equal to rho G H1 minus H2. We assume that, by the way, H1 is greater than H2, but it doesn't matter. Whatever you choose, the equations will come out to be the same. Okay? We assume that the flow is from in this direction. So over R, well, here I will be using RF1, okay, because I'm using the rho G term. Now this term is, I will call it 1 over R1. So Q out is going to be H1 over H2 over R1 as I have written here. Is it clear now?
Yes, hocam, thank you.
Okay, and the same thing applies to the second tank. As I have said, I assume that the flow is from tank 1 to tank 2. Therefore, we have to assume that P1 is greater than P2. You know, actually, in the actual case, it might not be greater than P2, might not be greater than P2, but it doesn't matter. Our equations remain the same. In that case, the flow will be in the opposite direction, and P2 will be greater than P1. As I have said, our equations will remain the same. It won't make a difference. Anyway, let's collect the terms in these equations. A1 dH1 dt, the first equation, plus H1 over R1 minus H2 over R1 equals 0. No, not 0, I'm sorry. It is Q in. Q in of T. This is the first equation. And then you have A2 dH2 dt now we have H2 over R1 here, H2 over R2 here with negative signs. So you have 1 over R1 plus 1 over R2 H2 minus H1 over R1 is equal to 0. And this is our second equation. Okay. So we have two first order equations, two first order differential equations, as you see. If you want to find, let's say, transfer functions, you replace, again, the derivatives with S terms. You can do that. For example, let's say we find the transfer function H2 of S divided by Q in of S. So what we do is we replace d by dt with S terms, and we will have the following. two equations in H1 and H2. Now, these are actually two equations, as you see, two linear equations, which can be solved by Kramer's rule, or you might, solve for H1 from the second one, substitute into the first one, and then solve for H2. Both are possible. I don't want to do the details. I'll just give you the result. For example, you can solve for H1 from equation 2. Substitute into the first one, solve for H2 over Q in, let's say. Okay, so this is our equation 1, this is our equation 2. And if you do that, you will get the following. You might try to do it yourself if you like. It will be what? And you will have 2 here. Where it is the kind of combined effect of R1 and R2. Okay? R1 and R2 in one will be series or parallel or something like that. Anyway, this is what we get if you solve it like this. I guess the easier way to solve this is to use the Kramer's rules, perhaps. Okay. If you do that, you get an easier solution for H2. Possibly. Okay. So one last thing before we stop. You can connect your tanks in a different manner. For example, you might have the following. You might have one tank flowing to the other one. So you might have Q in, and the flow from one tank might cause the flow to the other one. Let's say this is R, this is Q. We have to put a resistance here. This is R1, this is R2. So this is H1. This is A1, this is H2, A2. Now there is a difference here in these tanks. In the first one, the flow in the height in the second one does not influence the first one. You see, this is tank 1. This is tank 2. Tank 1 is independent of tank 2. Whereas this one is dependent on tank 2. Tank 1, I'm sorry. So the equations show this. For example, you are going to have A1, R1, DH. How will that be? Okay, let's just use A1 DH1 dt plus H1 over R1 is equal to Q in, will be our first equation. Whereas our second equation would be A2 DH2 dt plus H2 over R2 minus H1 over R1 is equal to 0. Okay. So you see this is the first equation, this is the second equation. H1 equation is independent of H2, but H2 equation is dependent on H1. This arrangement is called the gravity tanks. These are the second tank is independent on the first one. Okay, because the second one is influenced by the action of the gravity. It is not directly connected to the tank 1. All right, so much for the tanks and the liquid level systems. The next time I will be talking about hydraulic systems. That is another type of fluid systems. So let's stop the recording.